All right, there we go. Okay, welcome back everyone to our, I believe, first GeoDAWG seminar of 2025. Today we'll be hearing from Jiahui Hu. Before we jump into it, just a couple quick reminders to check out the GeoDAWG website. If you're not on the mailing list, feel free to join there. You can get updates about future presentations and other organizational things for GeoDAWG throughout the year. And if you have any suggestions for who to speak, including yourself or others, feel free to contact us with that information so we can schedule that. And then these are all recorded, so you can check them out on YouTube later on for your own reference if you want to go back and see something. And so with that, today we'll be hearing from Jiahui Hu. She's from Embry-Riddle Aeronautics University as a postdoctoral researcher with a background in data assimilation in at least ionosphere models, and I believe also upper atmosphere, if I read some of your work correctly. Feel free to ask questions throughout as they come up. And today we'll be hearing about improving data assimilation algorithm empire via data augmentation and common smoother integration. So thank you, Jiahui, for speaking to us today, and feel free to start sharing your screen and take it away.
Sure. Thank you. Thank you for the introduction. Hi, everyone. My name. Oh, sorry. Let me share the screen right now. Could you see the screen okay?
Yes. Yeah, we see it in PowerPoint now. If you go ahead and share. Thank you, David, for the mention about the IAGA session. We can put that up at the end on the slide too. But Jiahui, your slides look good, so go ahead.
Yeah, sure. Great. So first of all, let me briefly introduce the motivation that drives our study. Majorly is due to the geomagnetic storm, which refers to the energetic particles emitted from the sun interact with the Earth atmosphere. So it compresses the Earth's magnetic field and impact the atmosphere that we are living with. So this is the video that can show how the particles that can compresses the Earth's magnetic field lines. So one significant phenomenon that observed due to the storm by Dr. Dada Barua, my PhD advisor, is that she observed the nighttime atmospheric localizing enhancement, or abbreviated as NILE. So it is unusual because the electron content during normal nighttime is dimisible. And during the storm time, the intensive sun activities can excite the Earth ionosphere. It increases the charged particle drastically and lead persistent enhancement even during nighttime. So it can cause some signal delays. For example, the picture shows, one storm event happened on October 31st, 2003. So there's a persistent nighttime enhancement happen around Florida region. And when the JSON satellite passed through the Florida, we can see the signal delay can even reach to 12 meters. So understanding this phenomenon is essential because it can potentially threaten our lives. The technique that we be using is called data assimilation, which combines the climate models and measurements. So it can present more realistic information about the ionosphere. This circled region is what we call the Nile. So here, let me introduce the major components of data assimilation. So as mentioned before, it can integrate the information from the climate model and measurements. So the model can be either physics-based or empirical-based or combined, and the observations can be obtained from ground instruments such as LiDAR, radar, sonar, or airborne instruments, or satellite measurements. The two types of the information source, the model runs and the observations, can carry the uncertainties that defined by the covariance matrix. So which in the components here is the model errors and observation errors. So all of this information are fit into the assimilated method and can be categorized by variational, sequential, or hybrid method. So which is defined by the different state estimation algorithms. Then after the optimal atmospheric states are calculated, it can be put into analysis to investigate the physical phenomena. So in this presentation, I will be showing one sequential based assimilation method that has been developed for a decade. It's called estimating model parameters from ionosphere reverse engineering, or co-empire. So there are different data assimilative methods. So the empire is defined by attitude, geomagnetic latitude, longitude, and time. So each grid point represents the production, loss, and transportation of the charged particles. And the physical equation is formulated by the what we call the ion continuity equation. So it is showing on the right-hand side the which is the time derivative of the electron density, and the sum of the model term, which is A0, includes the production loss rate and the transportation term due to the diffusive and the gravitational effect, and the particle movements during neutral wind, 8U, and the E cross B drifts called AE cross B. Excuse me. So the difference between the measurements, the partial N, partial T, and A0 is the gap that we want to estimate it. So it is formulated as delta AU and the delta A E cross B. So this is the assumed to be the dominant gap between the observation and the model term. So which are due to the neutral wind and E cross B drifts. And this is the flow chart of empire. So the inputs is the SEMI3 and IDA40 assimilated with GNSS TEC measurements. And then it get time differenced to obtain the partial and partial T. And the model term will be subtracted from the time difference of the electron density. So which the gap is represented as Z. The mapping matrix HV and HU maps the E cross B and the neutral wind drivers onto, which are the delta XV and the delta XU, onto the ion density space. So this equation, the observation update, can optimally solved by the common filter technique defined in the empire. That will yield the E cross B drifts and the neutral wind drivers. So those two drivers can be mapped onto the velocity space by newly constructed mapping matrix, H perp here and HU. So denoted that they are only get mapped onto the space that represent the difference between the model and the observation. So therefore, to calculate the optimized ion drift and the neutral wind, the model values need to be counted. So this dashed box shows the major flowchart of the empire. And the climate model source can be different source. Here we use the SEMI3 data in IDA40. And other climate models are that we using is a horizontal wind model and the MESIS for temperatures. So from the previous findings, when we analyzed the empire performance, we found out that the empire will be consistently yielding larger arrows at high latitudes, while smaller arrows at the middle latitude. The high latitude arrows, due to the quiet time, are smaller than the storm time. That was the previous findings that we wanted to develop the empire to reduce the high latitude arrows. So one way that we proposed is to ingest the ion drifts measurement at high latitude. We'll be conducting an experiment on the storm event from the March 16th to 18th, 2015. So we will be augmenting the mid to high latitude measurements provided by SuperDARN, and in one is there are two file types. One is the fit data, and another one is the grid data. So fit data is derived from the raw measurements represented by 3D information of the atmosphere. So by removing the arrows in a project onto a horizontal space, we can get the grid data. So the total number of fit data is about 20 times more than the grid data. So after simulating these data source independently, we got two sets of ion drift calculations. So each of them will be validated against the milestone hail data, incoherent scatter radar measurements, and two other SuperDARN sites. And another approach that we propose to develop the empires, we have implemented the common smoother for reducing the arrows at high latitude. So first of all, I will be introducing the first one is the data augmentations of the SuperDARN measurements. So here is the figure shows how SuperDARN radar works and compare with the milestone hail radar. So the SuperDARN, which can emit high frequency signals to the atmosphere, and the signals will be get reflected only when the signal is perpendicular to the magnetic field line. So as here we can see only the red line here means when the signals are perpendicular to the Earth magnetic field line, represented by the white arrow here. But for the milestone hail, the MISTAR radar, it emits the very high frequency or ultra high frequency signals, and can get the signal refracted at any pointing angles. So adapt to the radar measurement property, the new observations matrix are constructed for different experimental cases. The first case is the baseline setup. So sorry, I think I jumped it one. Yeah, sorry. I think I jumped one slide. So the first case is the baseline setup, which is the parameter estimation without ingesting the ion velocities. The second case is augmenting the fit SuperDARN data. And the third case is the augmenting the grid SuperDARN data. So each of the mapping matrix will be reconstructed based on the radar properties. So first of all, we decompose the velocities measured by the SuperDARN, because it is perpendicular to the magnetic Earth field line, so we can project onto 3D space and represented by the Earth's magnetic field line coordinates. So the first setup of observation matrix is shown on the right-hand side, which is the difference between the measurements by SuperDARN and minus the model values yields the projected velocity by the newly constructed mapping matrix HVL fit and the E cross speed drivers. And the second one we project onto the geomagnetic coordinates, and then constructed another corresponding mapping matrix. So after the system observation system is set up, we fit the information here, and as this flow chart shows, we got the semi-3 IDA40 data and then get finite difference into the algorithm. The black color text indicates these are the previous or original setup, and the red text indicates the new augmentation that we are currently presenting. So the gap between the SuperDAR measurements and the background information will be fit into the common filter, and the observations will be stacked up to the uh, partial and partial t, the electron density rate information, and the corresponding mapping matrix will also be updated in order to map the electron E cross B driver, the delta XV, onto the SuperDAR measurement space. So after the calculations, we compare the E cross B angles with the mid to high latitude measurements. So this is the slide showing the storm time information that we will be ingesting. So left-hand side shows the DST index, which the 16 to 17 is the initial phase, and the data that we'll be ingesting is from the 17 to 18 during the storm time. So up around 22 UTS on 17th is the main phase, and afterwards is a recovery phase. So here I show the the left column is the main phase, and the right column is the recovery phase. So as the GNSS measurements indicates, there's nighttime enhancement near Florida for during the recovery phase on March 18th. So as the GNSS indicate, there is nighttime enhancement existence. So therefore, we analyze the storm event. And first of all, we gather the information from the semi-3 and IDA40, which is the source of Z partial and partial T here. And on the right-hand side is the SuperDAR coverage. So there are about 12 sites that we have been ingested, and the blue vectors are showing the coverage velocity vectors, and the magenta stars here shows the site that we be ingesting, and the red triangle are where the Milestone Hill radar locates. So after the information being ingested and after the calculation, we analyze how Empire calculating the ion drifts at mid to high latitudes. So these two plots are the line plot showing from March 17th to 1811 UT time. So the top plots are the field perpendicular zonal ion drifts, and the bottom plot are the field perpendicular meridional ion drifts. So different colors represent different cases. The blue one is the primary base case, and the magenta is the model value, and the brown color is the case 2. Here I ignore the plot of the red line, which is the case 3, which is ingesting the grid data, because it yields the worst result. So here we compare the result from the primary case and the model and ingesting the fit data. So as here we can see when Empire ingesting the fit data, it is more closer to the measurements represented by the black line, and yields the smallest zonal mean, smallest meridional mean errors and residual sigmas in both directions. The model performs the best for the zonal mean direction. And the case 3 is the worst case, which is only ingesting the grid data, and the case 2 are the other best one among those 3 setups. So then we compare the data with the Sapporo sites. We compare 2 sites, which is the CAP site and the SEX sites. So both of them are located at a magnetic latitude of 60 north. And we compare the result, but we cannot conclude which one performs the best for because they yield different values. So here we found out some key points is that the spatial information can potentially improve the driver calculations at magnetic mid-latitudes. So when we validating with a milestone hill radar, the Empire case of ingesting the fit data, which is 20 times more data, yields the lowest mean errors and the error sigma in the perpendicular meridional directions. But when we validating with the measurement from the Sapporo, no significant improvement was shown. So we could only conclude ingesting more data at a high latitude can help with the mid latitude calculations, but still we have larger errors for high latitudes. So another thing that we tried is to we implement the common smoothers, which refers to redefine the state calculations after the first round of optimal state estimations. So at initial step, we obtain a guess of the state, represent the delta x10 and the p10. So after a set of common filtering process, we gathered a set of outputs of the estimated states and its covariance. Then it will be fitted back with the information that we already have and with a measurement to redefine or recalculate the state, the atmospheric states, which are the neutral wind drivers and ion drift drivers. So this is a conceptual flowchart of the common smoother setup. The equations can be found in my thesis. So this setup could potentially improve the state estimation, possibly in the high latitudes. So to testify this method, we use a synthetic study. We haven't applied into the storm time, but we use the synthetic study for during the So we used the synthetic study during the same time of when we analyzing the Empire performance. So this is the flow chart of when we implementing the common smoother, and the only change is we not only we use the common smooth filter, but also we use the common smoother. And the other setup are exactly the same. So to compare the difference between whether coupling with the common smoother, we use a synthetic study from August 25th to August 27th on 2018. So to compare with the previous study, we found out when we couple with the common smoother, we reduce the error at high latitudes. If we can recall the several slides ago, we have more excessive errors at high latitudes. But after the common smoother, we have much smaller errors at high latitudes. Also, for time-wise, the storm time also have lower errors during storm time. And for it is for both directions, the perpendicular zonal directions and the perpendicular meridional directions. So this could be a good indicator when we implement the common smoother. It can potentially reduce the errors by several magnitudes. So we by trying different approach to reduce the high latitude errors, we can see that ingesting more information can help with the mid latitudes calculations, and implementing the common smoother can reduce the errors at the high latitudes. So we propose to continue developing the common smoother to improve the high latitude calculations in a real storm study for getting more valid information about storms, so that we can investigate the scientific phenomena of Niles. So this is all. This is my presentation, and thank you for being here. And this is my reference slides that that used in the presentations. And yeah, thank you all.
Cool. Great, thanks very much. Do we have any questions from the audience? Do you mind going back to your future work slide real quick? Oh, David has a question. Go ahead.
You go first, and then I'll follow up. It's all good.
Okay. Yeah, do you mind showing your slides again?
Yeah, sure. Oh, sorry. I think I just jumped to the last page. Could you see the screen right now?
Yeah, we can see it. I was just curious about your future work slide
Oh, yeah, sure.
with the other side.
Yeah, sure. Future work.
So just to make sure I understand, this is specifically with SAMI 3, right?
Yes.
And how
Semi-40 data. Yeah.
okay, how difficult would it be to implement in some other models to improve the other similar models?
Yeah, so currently my PhD advisor, Dr. Dada Barua, she is implementing the TaiGCM
Hmm.
data. So she's also doing similar analysis for the storm and the quiet time to see how the TIGCM will be showing the results of the ion drifts and the neutral winds. So
Hmm.
yeah, it can be used the other climate models.
Sure, cool, thank you.
Yeah, sure. Thank you.
I guess I'll ask the question I was having. So I guess Millstone Hill is a bit low in latitude for super darn. Um, have you considered looking at some of the ionosome drifts, drift measurements from all of the global network of ionosomes?
Ion zone drifts. We haven't tried it, but it would be a good validation source. When we trying to search for the validation source, we have some brainstorm some events, and we found that there's limitations source of validations. So that's why we picked Milestone Hill because it has more measurement. But yeah, we can definitely try to use the ion zone trails to do the validations.
Yeah, or
You mean
even for assimilating. But they're
oh,
usually
oh,
co-located with most of the Fabre Perots that I know that people have used with Empire in the past as well. So there's probably some interesting work that you can probably tease out by trying to assimilate the ion drifts from the iosomes.
and- yeah, sure. That would be a thank you for the suggestions. Yes, I will talk to my advisor in the mention the ion zone trails. Thank you.
Thank you.
Thank you.
Cool. Any more questions? Okay, well, we can thank our speaker again. Thanks very much for joining us today and sharing your work.
Thank you. Thank you. Thank you so much for your time, for being here.
Okay. And also, I'll throw up a quick slide real quick, just to share on the screen for everyone what David shared in chat a little bit earlier is that, hopefully it's showing the right screen, is that I believe this is the right session, but GeoDAWG will be hosting a session at the joint IAGA IASPEI. I don't know what that stands for actually, but the joint conference coming later this year. And so if you want to spend some of that, then make sure you get it in before March 12th. Okay, so thank you again, everyone, and we will see you next month.
Thank you.
Thank you.